Hey guys, I hope you're having a great Wednesday. So this video is to help you guys study for your test, your Unit 4 test that is this Friday. It was moved from Thursday to Friday, so please take this opportunity to be able to focus on studying and not just another day to chill. By this time, all of you guys should have done your acids and bases review packet. So for the most part, for my classes, we've gone over most of the packet, or we will finish going over it tomorrow. So on the first part, this got a lot of you. You were supposed to fill in. You were supposed to add more of the molecules. So the biggest thing I want you to take away from this is acids. Acids have to do with the hydrogen and the dissociation, the ionization of hydrogen that carries a ionic positive charge. You'll notice that with my first section here, the strong acids, that all of them are separated. That is because he's strong. So strong always has a high number of separated, pulled apart, dissociated, ionized of the elements. Then you would notice in the weak acid that some of my hydrogen are still attached to the other elements. So he's weak, but he still has hydrogen. Then strong bases, you'll see the OHs, hydroxide. They have ionized and dissociated from the other molecules as well, and they're running around trying to find hydrogen to bond with. Then weak bases. So same principle. So because it's a base, it's going to have hydroxide, but a lot of them stay with M. Now, M is not an actual element on the periodic table, but more a representation of just a symbol like A is for other elements that could be attached to hydroxide. So there's a lot of them that are still stuck together and not many hydroxides by themselves. So please understand the difference between strong, weak, acids, and bases. All right, so this chart here should have been pretty straightforward for you to fill in. The hardest part that I saw was today with the number 15 and 16. Tend to have a high concentration, so acids have a high concentration of hydrogen and a low concentration of hydroxide. Then bases are the reverse. They have a low concentration of hydrogen ions and a high concentration of hydroxide. All right, you guys should have been able to identify the differences between Arrhenius and Bronsted-Lowry models. Those are the two models that we needed to focus on within this unit. So just to sum it all up, Arrhenius is literally the ionization of hydrogen for an acid, and an ionization in an aqueous solution, a water, with for a base is going to be hydroxide. That is the major difference or major fact for Arrhenius. While Bronsted-Lowry is all about the donating and accepting of just that hydrogen. Now remember that hydrogen is a proton. It is the first element on that periodic table. So when you see proton, a proton, meaning singular, he's referring to hydrogen as well. So number 20, you needed to pick one. All right, so conjugate acids, conjugate bases. A lot of people had some questions on it. Totally cool, totally fine. I do want to explain some of this. So the conjugate acids, conjugate bases come from Bronsted-Lowry's model. So because his model stated about the donating and receiving of hydrogen, thus they're going to have a pair who they donated to, where their hydrogen went, and also what he becomes, the subspecies. So let's talk about the first one. And I have my board. Trying to figure out the best way. Here we go. So when you have an acid, with a base, there are going to be subspecies. You're going to either have a conjugate acid or a conjugate base. Now, some of you guys still think that acids go with a conjugate acid, which I understand your logic, but here's the thing. An acid conjugate is always going to be a base. The reason for that is it's not always a one-way arrow. It's a two-way arrow, meaning that the reactants become products, but also the products can become reactants. So when Bronsted-Lowry's model states that an acid gives up a hydrogen, the base is who's going to receive it. Now, if I flipped it, and instead of having, yes, it's upside down, I understand. Instead of going from acid bases to conjugate acid, conjugate base, if we all of a sudden reverse this and our reaction is going this way, the base here is the one who received it because he gave it up, but he's going to have to receive it to become the acid again. That's why the conjugate base is going to be paired with the acid for the reverse reaction. Now, the base gave up, it took in a hydrogen. His pair is always going to be a conjugate acid. So for number 21, should have been base. Then for 22, should have been a conjugate acid. Trying to make this a little smaller right now. All right, so let's talk about 23. 23, I'm going to write out the formula so we can discuss it. You have HClO4 plus H2O, H3O, hydronium, plus ClO4. So one thing to realize, everything on this side of the arrow, your reactants, has to be classified as an acid or base. They are both on the same side. You do not ever have a conjugate acid and an acid on one side. You always have an acid and base. So first, let's identify where the hydrogen is, who the hydrogen is leaving from. So you'll notice that ClO4 has a hydrogen, but over here, ClO4 doesn't have a hydrogen. So that means this guy right here is going to eventually leave ClO4 and become by himself. That ClO4 is the subspecies of HClO4. So that automatically means that's his partner in crime. That is his conjugate. Now, Bronsted-Lowry's model says that an acid donates hydrogen. So, HClO4 gave up a hydrogen. Goodbye, hydrogen. To become that. So he, HClO4 is my acid. And Cl4 is my conjugate base. So H2O gains the hydrogen, which let's put him over here. Eventually, he gains the hydrogen. So because he gains it, he is our base on this side. And his partner in crime is going to be hydronium, H3O. So because he was a base, his partner is going to be a conjugate acid. Okay. Hopefully you guys are not just looking at my answers and writing them down, because that would be lame, totally lame. So make sure you guys are looking this over. So if you still have problems tomorrow, please let me know, but you should be able to identify. First step, identify your acid. He's easy. Who loses the hydrogen in this entire equation? Who takes them on? The base. So identify the acid and bases in the reactant side. Then the conjugates on the product side. Okay. So these were pretty straightforward. Lemon juice, acid, detergent, base, bleach, base. I know it's weird to think of bleach, a base, but yes, it's a base. Vinegar, acid, coffee, hint, hint, wink, wink, coffee is an acid. Tap water. Now, I put this as neutral. Now, remember that pure water or bottled water, distilled water is going to be a pH of 7, which is neutral. But the tap water never really defined what was in the tap water, if it had extra calcium, if it had this, if it had that. So I just put neutral on the safe side. But some people are like, oh, Ms. D, it could be like a base, it could be like an acid, which I totally understand your logic on that. So didn't argue it, just defined it a little more. Soap, base. pH of 9, he's going to be a base. All right. And the pOH of 9, pHs are going to be 5. Just by the way, I added a little extra on that. Soda, acid, baking soda, base. And I know a lot of people miss that because you're like, oh, but it reacts with vinegar. Exactly, it reacts with vinegar. So remember that bases react with acids. Acids can react with bases. They can also react with metals. But a base cannot react with a metal. What it can do for a base is react with an acid, which think of all your awesome kindergarten science experiments with vinegar and baking soda and it going everywhere. So that is one way to remember that baking soda, base. pH 3 is going to be an acid with a pOH of 11. And tomato juice is an acid. All right. So this is just my pH scale. You guys could have different ones for your examples. The purpose of this was the fact that it was supposed to go from 0 to 14. I added a little extras, like the fact that this is neutral, the fact that on this side of the pH scale, 0 is 100% ionized of hydrogen ions, and the pH 14 would have a 100% ionized of hydroxide. So just remember that your strong acids and strong bases are actually at your start and your finish of your scale. They're on the outside. And then your weaker ones are towards the middle. And the guy in the dead center, your number 7, is neutral. And he has an equal concentration of hydrogen ions and an equal concentration of hydroxide ions. Okay, he literally is the tipping, where if this is, let's do this side. If this is acid, this is base. So right now, for an acid, hydrogen ions are great, but hydroxide ions are very, very little. And as it gets closer to the middle, When it reaches 7, they have an equal number. Then when it moves to the basic side, all of a sudden OH becomes greater and the hydrogen ions become a lot less. Another great visual example of this is this amazing infograph. If you want to pause the video and just to look at this, absorb the information, because this is one of the best graphs. So the red dots represent hydrogen ions. And you can see with our number 7 here that it has a 1-to-1 ratio, that there's equal red and there happens to be equal blue, hydroxide, OHs. And on the acids, there's a lot of red and only a little blue. Then on the base side, you'll see that there's a lot of blue and only a little red. So that means it's going to have a lot of hydroxide and a little hydrogen. And the acids are going to have a lot of hydrogen and a little hydroxide. So every time you step down the numbers, when you go from a pH 0 to a pH 1, you're literally, what you're saying is, hey, I have 1 times 10 to the negative 1 moles over liters of that, and of that concentration. So every time it steps down by the power of 10 and gets smaller amount. So right now at 0, acid is like crazy full with hydrogen. And bases, when he's at pH 14, is crazy full of hydroxide. So you'll just be able to see, you can see different fruits, different stomach acid should be around a 2, if I remember off the top of my head correctly. Soaps, detergent, everything like that is going to be a base. He's on this side. So it's just a really good infograph for you guys to look at. All right. So something I know I did in my classes, I added on our pH scales concentrations. Acids have a higher concentration of hydrogen, lower concentration of OH. In the middle, they're equal. On the base, it's going to be a high concentration of hydroxide, low concentration of hydrogen, and just labeling the acid and base side. All right, so concentration of hydrogen. You literally get your pH number by the concentration. What do I mean by this? Well, little ones, this is what I mean by it. If you have a 0 concentration, a 10, you will be a pH of 0. If you have 10 to the negative 1, you will be a pH of 1 for the hydrogen ion concentration. Again, if you have a 10 to the negative 4, you will be a pH of 4. Seeing the correlation, guys. If I have a pH of 7, I'm going to have a 10 to the negative 7. If I have a pH of 13, I'm going to have a 10 to negative 13. There is a direct correlation between the pH number and the concentration. The brackets that you see right here, bracket, literally represents concentration amount. Okay. That was not what I wanted to do. There we go. All right, so in this graph, in this chart, let me rephrase that. So it's stated that you have a concentration of hydrogen of 1 times 10 to the negative 2 molarity. And remember that molarity is moles over liters. So if he has a negative 2 power, he's going to have a pH of 2. Now, the third column here is asking for your pOH. And the really cool thing is the pOH scale is the opposite of pH. So we know that pH and pOH together, the entire amount of them, make up 14. They make up this whole graph, this whole scale. So if I have, let's see, if I am right here for pH 2, that means that my pOH is going to be the opposite of that. You just take 14 minus 2, which gives you 12. If you can add and subtract, you can do the math on this test. This is going to be an easy math test. Can you subtract? Yes. Beautiful. You're going to be golden. All right. So think of the pH. pH 2 should automatically come up as an acid. Next row, number 44. So I was able to know that it's 1 times 10 to the negative 4 concentration of hydrogen ions due to the fact that my pH was 4. Now, POH, if I'm trying to find my POH and I have 4 pHs, that means all I have to do is take my 14 minus 4 and equal 10, which is an acid. Now, please do not just copy these. I hope you are studying them because I will find out on Friday when you take your test. All right. So the rest of these are just comparing which one's facts about them, characteristics. So which one's stronger, pH of 4 or pH of 8? 4 is acidic. All right. Well, not acidic. I'm sorry. It's farther on the scale. So 4 is here. 8 is here. 8 is closer to 7. 4 is the winner. So again, number 57 is 12 versus 5. So 12 is out on the outside here. 5 is right here. 5 is closer to the middle. So 12 is the winner. All right. So weak. Just do the opposite of what I just told you. So the brightness of a light bulb. This should be an easy one for you guys. Remember that the more ionization that you have, the more charges you have running around, and the more that currency can flow through the aqueous solution. Thus, stronger the acid, stronger the base, greater the light bulb, smaller the acid, smaller the base, so the weaker it is. That means there's going to be less for it to travel the charge through within the aqueous solution. Thus, it's going to be a lot dimmer. So, strong, any strong, acid or base, bright, weak, is going to be not very bright. All right. Oh, you guys should do this one easily. Partial dissociation. Okay, red versus blue. You guys got that. Okay, last sections. Here we go. So just identifying which one's an acid, base, and neutral. This is going to be very, very important. Just being able to know the differences of the soda, lemon, hydroxide, and Drano. All right, so which of the following only contains bases? And I went ahead and ID'd all of them so that way you can visually see the question. It asked you, which ones are going to be only base? Well, coffee and hydrochloric acid is going to be acids. All right, then soap and vinegar. All right, you got one base, but the vinegar, totally acid. Then you have bleach and drain cleaner, and both of them are bases. Win-win. All right, and then just by the way, stomach fluids. You have a lot of stomach acids that help break down those amazing foods that you like to eat. If you're a total foodie, then you know what I'm talking about. And soda acid. So, all right, neutralization. This got some of you guys because it was the last thing we learned last week. So just making sure that you understand the structure of it. So when you have an acid burn or anything like that, you can't just put water on it because what happens is it dilutes it. It doesn't neutralize it. So what has to happen is you have to take a base, and a great base is to use baking soda. So a lot of times labs, which we have talked about, will have a base and acid spill kit. I know that in one of my labs, someone splashed some liquid on it, and I know that it was in the acid section. So versus touching it or just wiping it with a wet rag, I went and got baking soda and I put it all over it to let it neutralize before I wiped it up. That is important to realize. So if you have a base that has spilled, using vinegar to neutralize it. Then if you have had an acid spill, you're going to use baking soda, which is a base, to neutralize the acid. So what is occurring is this. In the reaction of neutralization, try to get this going. You're going to have a strong acid, strong base, your strongs. And they always produce salt. So you're going to have a salt. Now remember, it's not just table salt. This is not salt that you just eat, even though it is one of them. It is one of those ionic, from being able to set up the ionic naming, the ionic formulas that we practiced last semester, the ionization, so ionic salts, plus H2O. This is a neutralization reaction, period. So whenever it says neutralization reaction, automatically think acid, base, reactants, produces salt plus water, not salt water. All right. So what they're asking is for you to write a neutralization equation in number 81 for hydrochloric acid and sodium hydroxide. So when you do that, you literally have HCl plus NaO to produce the salt and the water. So one, I wrote out what they gave me. They told me what I'm reacting. They told me what is going down. Now, just figuring out who's being paired with who. Well, first off, one, he says water. All of us should know what water is, H2O. All right, if you are a visual writer like me, go ahead and cross out what you just used. Here's one H. Oh, look, there's another OH. Goodbye. What does that leave you? Well, it leaves me with an anion and a cation. So, Na, positive 1, Cl, negative 1. Remember that your positives go first. So, sodium chloride ends up being our fabulous salt. All right. So number 82 is just a straight definition you guys are going to need to know. Anaphoteric is going to be literally a substance that can either, in a reaction, be either one, acid or base. He is Switzerland. Whatever he needs him to be, he will do it. Meaning that if he needs to receive a hydrogen, he will. If he needs to give up a hydrogen, he will. So that is why H2O is the universal solvent. He is flexible. He is neutral. He is anaphoteric. So please remember that. Naming. This got to a lot of you. So I wrote this on the board for some of my classes that we got to this section, and it seemed to help some. Maybe not everyone, but some. So you really need to know and understand naming. Understand that with naming of acids, there are two big processes. So first, the simpler one is the binaries. Binary. involves only two different elements. H2 does not count as a binary. That is still a diatomic. So it is two different elements. And if you still struggle with identifying that, look for the capital letters. Does the compound that you're given have two capital letters? Yes, it's binary. Oh, it has three, not binary. Count the capital letters. So on our first, let's go to a good one. HI. Here we go. Hydrogen. Iodine. Let's talk about it. So you have H and you have I. Now, binaries are pretty simple because they're all structured the same. The first part, they're going to always have hydro. Then they're going to leave a blank spot forever who this guy's prefix is. Then he's going to end with an IC. Now, because he's an acid, all acids like to have their last name. They like to be identified as an acid. They are a proud acid. So, you end the binaries with acid. So, iodine, IOD, leave the INE, and you have hydroiodic acid. All right, so if you guys can write out this part, hydro space ic, hydroic acid, take whatever element that's in the second spot, sulfur, phosphorus, bromine, any of those, and add the prefixes of them, their stem prefixes, the starting point of them, you will be able to find that. Hint, hint, wink, wink, underline, because I saw a lot of this on the quizzes. Guys, this is one word. You are not spacing it out. It is not hydro, IOD, ic. It is all one word, one beautiful word together. And then acid. All right, so the next ones are a little more challenging because, and it's not a scary thing, if you just get into the pattern of doing this, it makes it a lot simpler. Polyatomics. Polyatomics are going to be able to have literally 3 or more, so not binaries, to be able to name. So polys come in 2 forms. Now, please remember that polyatomics are listed on the back of your periodic table. You did not have to memorize these. Thank you so much of you guys who decided to memorize some of them and had panic attacks. No, they're still on the back of your periodic table. So let's go ahead with the first one. So the first one. All right, we have HNO3. So first off, HNO3 has 3 capital letters, H, N, O. He's binary. Now, flip to the back of your periodic table. Look and find the polyatomic for him. So you'll notice that he ends with that you should have found on the back of your periodic table that NO3 is nitrate. Nitrate. So the fact that he's nitrate, we take literally the ATE, just the ATE, and say goodbye. And you're going to replace him with ic. And he becomes nitric acid. Again, last names are important. Like Ms. D, Devaney, my last name. It is important to me. All right. So for number 83, nitric acid. So this is the first polyatomic type of the namings that we did. So when you take an ATE to an IC, at 8, ic, All right. The next kind is going to be also a poly, but he's a little different. So I'm wiping off my board. And let's use HNO2. Again, when you see this with his chemical formula, you should notice, oh my goodness, he has 3 capital letters. He is polyatomic. All right, so identify who your polyatomic is, NO2. So when you look on the back of the periodic table, you should see the name nitrous. All right, so for his polyatomic, his ITE becomes OUS. So write out his name, circle his ending, cross him off, and write it with OUS. NITROUS. Acid. Nitrous acid. Now, think back. Did I put hydro in front of any polyatomics? No, I did not. Hydro, when you write out his chemical name, only goes with binaries. So when I have hydrogen and bromine, that becomes hydrobromic acid. Hydro only goes in front of binaries. Polyatomics like to fly solo. They do not need a hydro. But the fact that they have acid at the end still identifies them as an acid. So you don't need the hydro in front. All right, guys, you should be able to practice this. All right, that is a pretty strong summary of the review guide. If you guys have any other questions, we have all Thursday. Please, 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 please ask me. Don't hesitate. There is no dumb questions. It's only dumb not to ask questions. So, again, I think I showed you. Oh, great picture. Love pictures. Visual learner here. Kinetic learner. All right. So again, just the differences between acids, bases, hydrogen concentration, hydroxide concentration. So yeah. All right, guys, I hope you have a great night, and please message me if you need any deeper explanation for anything. I really, 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 really expect high and great things, and I truly believe that each of you can do this. Have a great night. Bye.